Imagine having a massive library inside your head. It holds every single thing you've ever learned, but there's absolutely no indexing system to actually find the book you need when you need it. Pretty frustrating, right? Well, that's exactly what it's like for AI. Stored memory is completely useless without the intelligent mechanics of memory retrieval. So, in this explainer, we're diving into the architecture that makes AI memory actually work. Which brings us to the core question. How does an AI actually remember you? You see, it doesn't just casually drag and drop everything you say into some giant digital folder. There's a massive difference between just hoarding raw data and actually recalling it efficiently. Without a proper retrieval system, an AI isn't really intelligent at all. It's honestly just an overpriced hard drive. Here's the roadmap for this explainer. First, we'll look at the AI memory problem. Then, we'll get into coding semantic search, followed by building out the hybrid pipeline. After that, we'll see how trimming saves you on API costs and wrap up with vector databases. All right, Section 1, the AI memory problem. Let's look at why naive memory architectures inevitably fail under pressure. Okay, let's dive into this. The absolute most common mistake in early AI design is blindly sending the entire database to the large language model. Because models have really strict token constraints, dumping all that raw storage into a single prompt creates this massive token explosion. The whole system just breaks down. The true intelligence layer is all about retrieving only the most relevant context. And this brilliantly mirrors how human memory works in our daily lives. Think about it for a second. Your working memory, the stuff you're actively thinking about right this very second, that's the AI equivalent of a conversation buffer. Trying to find broader memories based on a general feeling or meaning, that maps perfectly to a vector database. And when you're trying to recall an exact phone number, well, that's just your brain executing a keyword search. Moving on to Section 2, coding semantic search. Let's look at how we upgrade from naive setups to systems that actually understand meaning. So, there's a massive difference between keyword and vector retrieval. If we rely entirely on exact word matching, the AI is going to completely miss the broader meaning. For example, say a user's log reads, "User trades nifty options." If you ask the system, "How does the user invest?" a basic keyword search is going to fail completely because the words don't exactly match. Vector retrieval, on the other hand, uses semantic similarity. It understands that trading and investing are conceptually linked. It's like it actually gets the gist of what you're saying. And implementing this in code is actually surprisingly simple. It really just takes 4 main steps. First, you load up a model like Sentence Transformer. Second, you encode your text memory into vector embeddings, which is basically just turning the meaning of the words into an array of numbers. Third, you add those embeddings to an index like FAS. And finally, you run a search on a new query. Just like that, your AI is suddenly looking for mathematical closeness instead of hunting for exact words. Real game changer. Now, to actually do that, the AI uses similarity search math. Don't worry, it's not too crazy. You've got cosine similarity, which determines semantic closeness. Dot product is really excellent for ranking those results once you have them. And Euclidean distance measures the literal straight line distance between two concepts. Basically, this math calculates exactly which stored memory is nearest to the user's question. Which brings us to Section 3, the hybrid pipeline. This is where we combine all these individual techniques into one master architecture. Because let's face it, relying on just one single type of search isn't going to cut it. Modern systems use a hybrid retrieval architecture. It's the whole shebang. It combines a conversation buffer to keep track of recent context, keyword search to grab those hard, exact facts, vector search to understand the deeper meaning, and a long-term database for persistent knowledge. To put that into perspective, imagine a user asks, "What setup do I usually trade?" The AI doesn't panic and scan its entire hard drive. Instead, the buffer grabs a recent chat about stop losses. The keyword search extracts the exact phrase, "nifty options." And the vector search conceptually pulls up the breakout momentum strategy. All of that comes together to build a final prompt injected into the LLM that is cohesive, hyper-relevant, and most importantly, doesn't blow up your context window. All right, Section 4, trimming and API costs. Because retrieving memory doesn't just impact your AI's intelligence, it directly impacts your wallet. Let's look at managing this flow. Basic buffers use these really simple sliding windows, kind of like just saving the last 5 messages. The problem? They totally ignore token size, which scales poorly and risks context overflow. Advanced token-based systems, however, actively track the exact token count.
If your limit is 2,000 tokens, it surgically trims the oldest data until the package fits perfectly.
And believe me, you desperately want strong overflow prevention. When a conversation just grows forever without trimming, you hit a token overflow disaster. Inference times slow to an absolute crawl. Your API costs skyrocket because you're literally paying to process useless data. And worse, you get attention fragmentation. The AI gets so distracted by all those irrelevant past memories that it completely forgets your actual question. But implementing token trimming reverses all of that. Tighter prompts lead directly to much faster inference. The LLM can allocate its attention perfectly, which drastically reduces hallucinations and improves overall response quality. And, of course, your overall API costs plummet. Efficient retrieval isn't just a technical upgrade, it is literally a money-saving feature. And finally, Section 5, Vector Databases. Where exactly does the AI actually store all these long-term vector memories? Well, you have several specialized databases built exactly for this. Fias, for example, is absolutely phenomenal for local retrieval and testing things out. But if you need managed cloud vectors for a real-world production app, Pinecone is for sure the industry favorite. You also have Qdrant for raw performance, Weaviate for specialized hybrid knowledge, and ChromaDB for lightweight local builds. The key takeaway here is just matching the tool to your architecture's scale. So to engineer a truly scalable AI memory system, you want to follow these core rules. Number 1, never blindly send the whole database, only retrieve the relevant memory. Number 2, use hybrid pipelines so you capture both exact words and semantic meaning. Always trim your tokens to keep costs low and quality high. Make sure to rank and filter your results, and hey, always cache your common retrievals. We'll wrap up this explainer with a pretty powerful thought. Without retrieval, memory is just storage. With retrieval, memory becomes intelligence. The true magic of AI isn't in how much data it holds. It's in finding exactly the right piece of data at exactly the right moment. So looking at your own systems, what valuable insights are currently hiding in your data just waiting for a smarter retrieval system to unlock them?